Hello, everyone. Today I'm here to present our work on REIS assisted coverage enhancement in an urban setting. And I present this work um, under the supervision of my supervisors, advisors, Yap, Ricard, and Chandan. And this work was done together with Ziye, who is now with Ericsson. So, as we can see in the figure, in 6G networks, we are moving to higher frequencies than in the previous standards like 4G or even 5G. These higher frequencies, such as millimeter wave and beyond, offer significantly more bandwidth, which is excellent for data rates, but introduce a major challenge, which is signal propagation, because as we experienced in lower frequencies like in 4G and 5G, the signals can bend around the obstacles, as we can see, uh, as we would have seen in the case of 4G or 5G. But this is not the case in 6G networks because of the higher frequencies. The signal is more sensitive to physical obstacles. So even bad weather or buildings or trees can weaken or block the signal, which can create coverage gaps and reduce reliability in urban environments. Um, Here we can we the objective is to evaluate coverage and throughput performance in such scenarios, and the solution provided is a reconfigurable intelligent surface, which I'll be coming uh, to explain a little bit more. But in this figure, we can see that we have a base station which has maintained a direct path with some of the users or devices, but it has a blocked path in case of a 6G network to most of the users in the blind spots. Um, so the motivation behind this work, if we focus on a vehicle to everything communication in a dense urban environment, which is going to be a critical aspect of 6G networks. So where the vehicles maintain communication between the devices and the base station, in a V2X context, the base station allocates resources to a wide range of sensor devices that support vehicle safety and efficiency. For example, a vehicle's onboard sensor may receive real-time weather updates from the base station to adjust driving conditions safely. And similarly, vehicles can receive traffic congestion updates to optimize route planning. So, in these scenarios, we can see that a coverage gap can lead to a potential hazard, and we have to maintain a seamless connection between the devices and the base station. In this scenario, a reconfigurable intelligent surface can enhance communication by reflecting and modifying signal paths. So, what is a reconfigurable intelligent surface? We will call it a REIS from now on, uh, to be because we have short time. And in literature, also, the term adopted for the short term adopted for reconfigurable intelligent surface is a REIS. As we can see in the top right figure, a REIS is a planar surface. We can see the visual representation here. It is a planar surface that consists of passive reflective elements, and we can see in the bottom left figure that each of these elements is controlled by a tunable circuit, which can modify the phase or even polarization of the incident signal. In this way, the REIS can redirect signals towards targeted areas, enhancing coverage and signal strength. This adaptive mechanism allows REIS to operate in real time with minimal energy, making it particularly valuable for dense urban environment settings, where traditional signal paths are often blocked or hindered or may result in weaker signal strength. Uh, the applications that I have already mentioned are 6G networks in Internet of Things, vehicle to everything communication, vehicle to vehicle communication. So the applications are very vast. But of course, the REAS also comes up with its own set of challenges, and the biggest challenge is the need for perfect channel state information to accurately adjust the phase shifts of each REAS element. When we talk about theory, if a REIS could obtain continuous and precise CSI, which is done through a link, consistent physical link between the base station and the REIS. In theory, if a REIS could obtain that, the it could optimally reflect signals toward targeted receivers, maximizing signal strength and coverage. However, in practice, acquiring and updating this information in real time is complex, it is resource intensive and often impractical as well, especially in dynamic and high mobility scenarios like V2X communication. So, a challenge would be to simplify the protocol for of the beamforming protocol of the or the reflection protocol of the REES. It is also crucial for industry adoption because the industry is a little skeptical about the implementation and deployment of the REESs in the 6G standardization. I will explain a little about the system model here. We can see that now when we have come from the last figure to this one, with the deployment of the REESs are shown in the red. These are planar surfaces with multiple elements, and they can be, deployed in, on the facades of the buildings or as billboards. They can be deployed anywhere. The feasibility is very simple. But as soon as the deployment is fixed, we can see the reflections going around the blind spots, and we can see that we have coverage. In this system model, we have a single antenna base station. We have multiple single antenna users, and in our case, to maintain the symmetry of the map, which is a crossroad in a dense urban environment, we have deployed three REESs. The objective is to improve coverage and throughput using an autonomous REES reconfiguration protocol. So, autonomous REES presents a solution to the challenge of acquiring a CSI and obtaining and maintaining a link between the base station and the REES by operating without real-time channel feedback. So instead of relying on CSI acquisition, an autonomous REES uses pre-programmed phase configurations, or we would like to call that a code book, which is pre-programmed, and it sequentially and efficiently directs signals to cover specific areas corresponding to a specific geometrical angle. This approach allows for consistent and low cost coverage enhancement without the need for a dedicated control link between the base station and the REES. Um, this setup makes the REES highly practical and scalable because we can deploy as much autonomous REESs as much we can, depending on the ergonomics and economics of the system. And this is particularly feasible in urban applications where CSI acquisition would otherwise be a limiting factor. I've I to visualize the function or the configuration protocol of the REES a little bit more better. We can imagine a lighthouse on the sea, which casts its beam of light in a specific direction, illuminating only the segments of the cast one at a time, as it rotates through the hemisphere. So an autonomous REES also operates similarly in a sequential reflection mode. So it reflects its beam one at a time in a targeted area, enhancing SNR in that particular area. And this sequential operation ensures that each area where the beam is focused by, or the reflected beam is focused by the rays, uh, uh, we enhance communication accuracy and efficiency, much like how the lighthouse guides ships to navigate safely by illuminating only the required segments of the sea. In both cases, the lighthouse and the reefs, it's a very strategic and a controlled process where we deliver signals or lights to key locations at precise intervals. It is crucial to highlight that there is no feedback link between the base station and the rees in the case of an autonomously functioning rees. Sorry. I will explain briefly about the channel model. We can see that we have a single antenna base station, and we have simulated a Riccian fading cascading channel that simulates blocked or direct paths to between the nodes. With an autonomous REES protocol, we use pre-programmed codebooks for sequential signal reflection, and the known parameters in this case are the distance and the geometrical angles between between the base station and the rhesus. And we don't know about the true location of the user or the receiver, and we don't require that information because the autonomous REES directs its beam towards the entire map area and gets as a feedback the SNR at the base station. And on the basis of that, the base station the base station can make the decision about the scheduling algorithm, the scheduling decision. The objective here is to evaluate coverage and throughput after scheduling, and the scheduling algorithm that we have adopted is proportional fair scheduling, which is conventional. The simulation operates at 3 gigahertz carrier frequency with three rheses, and we have assumed that each rhes consists of 201 elements. So roughly speaking, the size of each rhes is in the order of a meter squared, or half is it is less than a meter squared. We have a uniform and random user distribution in urban crossroads, and there are 50 users per channel realization. We evaluate our work through the CDF of user throughput and also the coverage heat maps. The comparison scenarios are where one is where we have no REES deployment, the second one, which is the proposed autonomous REES, and the third one is the coherent beam forming REES, where the factor that the CSI has to be acquired consistently and without any break. The REES acquires that information about the channel state information and redirects the signals at the true location of the user. So here we can in the bottom we can see that in the bottom row we can see the CDF empirical CDF of the autonomous and no rees and also the coherent rees scenario. The blue curve shows the scenario where we have no rees deployment, and we can see that in this case, more than 40% of the users are starved. They don't have any coverage, and this is also evident in the heat map here. But as soon as we can see from the red curve, as soon as there is an autonomous rees deployed, we can see that all the users have coverage and no user is starved, but at the cost of the best users throughput. We can see that the best users sacrifice some of their data rate or efficiency so that the worst channel condition users may thrive. And this is owing to the scheduling algorithm that is the proportional fair scheduler. But the deployment of the rees enables the scheduler to strike that balance between the users and the throughput and the fairness. The third one is the benchmark performance, where the true location of the users is known. And we can see that the autonomous rees strikes a very low cost and efficient balance between no rees and real time reconfigured rees scenario. Um, I will conclude my presentation with the takeaways. We have shown that coverage enhancement in 6G networks is a key challenge, and it can be, there is a solution to it by deploying a REES, which is a low cost solution. And we can further simplify its reconfiguration protocol by eliminating the need to maintain a consistent feedback link between the base station and the rees, and eliminate the real-time adjustments. And with this low-cost solution, uh, coverage enhancement is still possible, and it is very feasible for industrial adaptation as well. Thank you very much, and I'll be glad to answer any questions.
Great, Faryal. Thank you very much. I'm looking in the Q&A. Let me see. There are no questions yet. One question.
There is one question
there
from
is one
Mikael
question.
about reflecting surfaces.
Okay, do I miss it? I have to scroll up. Yes. So the question is whether if you have these kind of reflective surfaces in the city environment, are city planning and architects, are they already in the loop, let's say? Are they aware of the need, or yeah?
That's a very relevant question. I would say that after the standardization, it is something that they are going to be in the loop, and they are going to be very much a part of it. That because then the engineers and the smart city developers, they need to work in collaboration to deploy the reses in the best positioned way, so that the performance is guaranteed, the performance increase is guaranteed. But
Yes.
for now, I'm not sure.